Well, good morning. My name's Derek Teasdale, and I'm a quaternary geologist or a glacial geologist. I look at the effects of the last ice age on particular areas. And as I've always lived in the northeast, I'm particularly interested in the northeast. And so the opportunity to work on having a look at Hadrian's Wall when it presented itself, it sort of really got my imagination going. I live in Hexham, and when lockdown started, I thought, what am I going to do? I can't travel very far. I need to have some subject to work on it. And the obvious thing was to look at the Tyne Valley and Hadrian's Wall. So I've actually been working on this like mad over the summer, and because of that, I've got a lot of interesting material which I'd like to share with you. But before I do that, I'm aware that many of you might not be geologists, and a bit like Ian, even if you are geologists, you've gone off on a bad path. You've gone to the dark side of solid rocks and haven't looked at the sort of things that I do. Okay, so that's my title picture, and you might be thinking there, when you look at that picture, you'll be thinking, oh, he's chosen that because it's a bog standard picture of Hadrian's Wall. Yeah, well, actually I've picked that because that is a spectacular example of a meltwater channel cutting through the wind sill. And if you can recognize the fort, I think it's Housesteads, and Housesteads is where it is, not because it's on top of the windsill, because it's not. It's there to guard that meltwater channel. Yeah, it's positioned right beside that little valley beside it there. Yeah, if they'd wanted to put it on a defensive position, they would have put it further away, further up where the cliffs were steeper. They know they put it there because that was a route way too. So we'll come back to this picture and many more like it. But I'm going to give you 2 slides to summarize all you need to know about the geology of the Roman Wall. Right? So let's go to this slide. Okay, so the rocks that make up the this bit of Northumberland are all slanting at a very gentle angle towards the south, and they're made up of various different types of rock, things like mudstones and shales, which are very similar rocks, are very soft. Sandstones and limestones are of medium hardness, and in the middle there's the famous windsill, which is an igneous rock. That means it was molten rock when it was emplaced between these different layers, and that we're going to say is very hard. So we have soft, hardish, and very hard. Okay, so that's one half of what you need to know if you're a glacial geologist. The second part of our and final bit of our hard, solid geology is this slide here. Now this is an aerial view looking down on the wall in the central sector, and if I just trace along, we can see the top of the windsill, and it jumps down to this sort of area, then it jumps across to this area, and it jumps backwards and forwards. And the reason that the windsill is jumping across is picked up by these dashed white lines, and there were some quite big faults. And our fault is a dislocation in the geology in the rocks. It might appear at first sight from looking at these dislocations that the rocks have moved from side to side, but in all probability what's happened is the rocks have actually moved up and down a little bit, and that's been enough to throw the top of the escarpment back a little way, moving it to either the north or the south as it goes along. So we've got some faults and we've got rocks of different hardness, and that's, you'll be glad to know, is the last of my hard rock geology for this. From now on we move to ice, which is my thing. Yeah, okay, so let's see if I can move to the next slide. Okay, let's do it like that. I'm just going to mute myself for a second while I cough. Right, okay, so here we have a nice image on the left of probably the Greenland Ice Sheet. Now, Greenland Ice Sheet from the surface looks like a very large white mass of ice extending off into forever. This is near the edge of the ice sheet as it goes through some mountains near the coast, and we can see mountains sticking up through the ice, and these are known by the wonderful name of being a nunatak, which is just a posh way of saying bits that stick up through the ice. On the right you'll recognize a snowy picture taken from the last bit of snow last week, when I went up to the wall, and I was just looking across, and we've got a little lake there and some hills in the distance, and just a nice snowy landscape. Okay, now if we were to think about the ice sheet on the left and ask ourselves, what does it look like underneath that ice? What does it look like at the base of that ice sheet? The answer is, we look at the picture on the right. Okay, the picture on the right is an entirely glacial landscape. We don't tend to think of Hadrian's Wall as being a glacial environment, but it is, and virtually every feature you can see in that environment, in that picture on the right, is actually produced and created by the action of ice moving across a combination of mudstones and sandstones, limestones and the wind sill, and with those faults. So basically we've just got a bedrock that is of varying hardness, and we've got a big ice sheet moving across. Now in terms of Hadrian's Wall, understanding where the ice was moving from and to is very easy. It was coming from the west and going due east, and that's pretty much a good approximation for everything you need to see in the Roman wall. Okay, so I'll just say a little bit more very briefly, oops daisies, about how ice and glaciers work. I'm not going to go very heavy on theory. There's going to be lots of pretty pictures. Okay. So these are our theoretical images of how an ice sheet works. In essence, an ice sheet is just ice flowing away from a place where it snows a lot. Okay, if you get a lot of snow, in winter usually it freezes, and if you get an excess of snow every year over the amount of melting, you eventually get it consolidates down into ice. Ice actually flows. It's not like water. It doesn't flow instantly, but it flows slowly, and especially when it breaks up into crevasses and things like that. And I've got some pretty pictures to illustrate this. And as it flows away from that zone where it accumulates, eventually as it goes further and further, it tends to go into lower areas where it doesn't snow so much, and eventually it wastes away and it reaches a boundary. And that boundary sort of marks a zone where you get piles of muck and rubbish and stuff like that all coming out the front. So we get a characteristic set of landforms which are produced underneath ice, and we get a characteristic set of landforms produced at the edge where all this muck and rubbish comes out the front. The landforms underneath the ice are relatively simple. The ones that are produced at the boundary are best described as stupidly complex, right? And very sometimes rather difficult to work out what's going on. You'd be glad to know that you get both sets of landforms along Hadrian's Wall in abundance. Okay. Right. Now you might be thinking to yourself, that I've oversimplified that message, yeah, that I've made it too dumb, that, you know, you'd have heard words about moraines and drumlins and things like that, and in a way, yeah, I probably have oversimplified it a bit, but you shouldn't overcomplicate it by sticking names on things. Glacial deposits are inherently incredibly complicated because they're just a mess. There's lots of mush and all sorts of things going on. So I'm trying to say, keep this as simple as possible, but also that's a really, really good way of working with glacial deposits. Just simplify all the time. And I'm going to hopefully show you how to recognize the deposits that we might see around Hadrian's Wall, so that you can recognize them, and you can do so in a simple way, right, which is really useful. Okay, so here's a picture of a glacier in Iceland. This is called Breda Mercurial. It's not actually called that, but that's my closest pronunciation of the Icelandic. Breda Mercurial is a very famous glacier for glaciologists because it's thought to be the closest analogue for the glaciers that affected the United Kingdom. It's a big glacier. It's quite dirty. It's got lots of water at its base, and as such, it appears to work as a glacier in the same mechanism as the ice that would have covered the Tyne Valley and Hadrian's Wall. So if you're going to think about what the ice looked like that crossed Hadrian's Wall, your best bet is to think about something that looks like this. Not the pristine whiteness of the center of Greenland, but the dirty and rather sort of mucky exposure that you see here in this rather amazing image. If you trace back the dark lines that go across here, these medial moraines, as they're known, going back up, they lead back up to nunataks or to mountains often. So this one here comes out there, yeah. And what's happening is that the ice, which is actually coming off the Vatnajökull ice cap in the distance here, is coming down and it's splitting on either side of some sort of higher ground. And as it goes past the higher ground, it's eroding those hills on either side, and lots of material falls down onto the ice. It gets picked up, and as it comes to the other side, so here's a good example, we come past, the ice then joins back up again, and it forms these moraines which run down. As we get to the front of the ice, we see the moraines here get dumped out as big piles of rubbish. Like here's a good example here. All of this material, it's clay, sand, silt, boulders, and it all comes out as a big mess. Yeah. Now we can call that lots of different names, and there is a whole terminology to call these things. You can call it till, boulder clay, moraine. These are words that are often used. Yeah. Now, don't be put off. A proper glacial person like me, if you turned around to me and said, Derek, that looks like, shrugged shoulders, a mess, right? And looked at some boulder clay, I would say, well done. You've spotted its main characteristic. It's a mess, right? That's a mess in there. It takes quite a bit of understanding to get a grip on it, right? Between the medial moraines, we get these little lakes forming in places where there isn't very much material coming out of the front of the ice. Okay, I'm going to quickly run you through some pretty pictures of various features you might see in the landscape. And I'm going to hold it together by just talking about three different things. One is features which relate to erosion. Then there's features which relate to deposition, and then there's stuff to do with water. And they're the three things you've got to think about when you think about ice. How's it eroding? What deposits can we see? And what's going on with water? Okay. And I've specifically tied this down to stuff we can see in Hadrian's Wall, and particularly the central sector for much of this stuff. Okay, so erosional features. What can we see? Well, the ice sheet carries a lot of mass at its base. It acts like sandpaper, and it wears down anything that sticks up. Any of the harder rocks, the sandstone and the limestone, or the very hard rocks like the whinstone, get smoothed off and eroded by the ice as it goes past. Yeah, and sometimes the scratches are put into the rocks as well. Okay, the softer material, the mudstones and shales, just get eroded away, destroyed, disappear, and that becomes the clay in the boulder clay further down. Okay, so let's have a look at some examples. So classic example here, really good example of this is a bit of bedrock or hard rock. It's probably some granite or gneiss or something like that in Quebec. And basically, as an ice sheet's gone over the top of it, it's smoothed it off and eroded it. Okay, so we can see loads of examples of this sort of stuff over Hadrian's Wall. Okay, especially on the whinstone. Yeah, the whinstone unfortunately has some really good joints in it, so it tends to get broken off and flows away. But at a smaller scale, you can see things like this if we're lucky. Yeah. Now, what I just want to point out to you is that this is smooth here, and it goes up to this spade, and then there's a sharp cutoff. Yeah. As bits here gets picked up by the ice and carried away, in what's called plucking. Now, at a bigger scale, we get something called crag and tails. Famously, Edinburgh Castle and the Royal Mile is a crag with a castle on top of it and a tail, which is the Royal Mile leading down to Holyrood. And this is just another example of a crag here. It's over steepened at one side where the erosion is taking place, relatively smooth over the top, and then the ice has moved off in this direction and it's produced this feature which runs down, and it perhaps extends quite a bit further. Is around here, and that's the tail. Now you'll also notice that around the crag there's a lake, and you can actually see water sunlight reflecting off water here as well. So around a crag and tail you get this sort of feature, which is like a glacial trough or a channel being eroded out. Yeah. So what we can assume is that this bit here is slightly harder and has resisted the erosion, and this bit's erosion's taken place around either side of it as the ice has been separated and pushed around either side where there's erosion. And then we get a bit of clay and mud and gunk and mess gets left in this very characteristic tail, which is formed by a release of pressure in the ice. As the ice gets squeezed in by the crag, it builds up pressure. As it releases the pressure, there's a bit of a cavity opens behind, and we get lots of deposits in there. Okay, so that's our features of erosion. Okay, so let's go back to the wind. Now, I told you before that as far as we're concerned, we can assume that the ice is going from west to east at all times, yeah? In which case the ice is actually coming from the distance in the west there and is coming along the escarpment, the wind sill. Yeah? So what can we see? What can we see here that might look like an erosive feature? Well, it's a bit iffy, this, because if we're thinking about it, erosion is really going to create crags. It's going to create bare rock. And yet, if I asked you to show me where the bare rock is in this image, you'd probably say, well, there's a cliff line here where the wind sill goes on. But I said, can you point to any bare rock here? And the answer is no, you can't. Right? It's actually very difficult to find bare rock in this supposedly eroded landscape. Yeah? So we have to work quite hard to find bare rock. For the most part, what we can see here is grass and vegetation. And if you dug a hole, there'd be mud underneath it. And below that, there's boulder clay. Yeah? So in actual fact, there isn't a heck of a lot of erosive material here. This is a small mini escarpment just to the north of the wall. And this one I think is sandstone. So what we have is a small sandstone outcrop here. It's been quarried. So this hole in front of us here it's been quarried. Somebody's been taking it for building purposes. And what we've got here is, again, we've got rolling, smooth landscape with lots of grass, lots of sheep. Everywhere you can see sheep, you don't have glacial erosion. The eroded bits, the exposed bits, is just along here. And again, we've got this low slope behind. We've got an escarpment and then a slope in front of you. Okay, so that, again, there's not a heck of a lot of erosion going on here. There's an awful lot of deposition. Okay, so this is to remind me to say to you that everything I'm showing you today, every image, all of the software and all the rest of it is all free, is all available, all of the data is available. I haven't spent a penny in any way on any of this stuff, and you can do all of this stuff yourself. This is Google Earth. This is an image of the wall, and we can see the wall tracking across in this direction. There's the escarpment again running around, and this is a view that's looking towards the west from the east. And I just wanted to point out to you the ridge. Here's the wind sill, but just look to the north. We've got another ridge running along here, and another one running there, yeah, and another one and another one. That image I just showed you was about here, I think, just up there, of another thing. There's loads and loads of mini escarpments or cliff edges, all running parallel to each other. The wind sill happens to be the big one, and it's the one you'll walk along a lot, But to be honest, if you want to understand the geology and the glacial geology, you're just as well walking along these ones over, which run parallel. And also they sort of tend to do a little sort of dance and they move around. But the other question I could ask you again is, could you point out, this is another image, this is, just trying to work out where and that's that same lock I was looking at before. So again, if I look at this and I say to you, where's the bedrock, where's the exposed bits of stuff that's been eroded away by the ice? Well, there again was a few little escarpments running along here, which are quite visible from the road and quite dramatic, and your eyes drawn to them. But in reality, when you look between them, there's a huge amount of grass. There's a huge amount of rather smooth looking surfaces. Now, if you erode away a landscape so it's just taken right back to the bedrock, you get a very rough, rugged looking landscape. Imagine mountains or in the Lake District and things, where all of the glacial material's been removed. You get quite a rugged looking landscape. This is not a rugged landscape. It's actually quite a smooth, mellow landscape in many ways. Okay, so this is, I'm just going to show you another image of exactly the same place. This one was taken, I guess it says up in the top there, it was on the 31st of December 2006. This is the same Google image, but this one was taken in July. I've enhanced the colors a little bit by fiddling with them in PowerPoint, but I've not done anything overly special. This is the same image in July. And there's another feature I want to just point out to you is, whilst most of the image is nice and green, we do get these areas like this one, and this area, and this area, and this area, which are quite brown in this image. There's also a lake there. Now these brown areas are peats, and where we're seeing different vegetation. We're seeing sort of rushes and sedges and bogs and things like that growing out. If I combine the two images together, we get a combination of quite nice indications of what the shape of the land is, but also we can see some of those colors coming out a bit better as well. So what we've got here are lakes, escarpments, and between we've got very smooth bits like this. We've got smooth, smooth, smooth thing. If you go round the landscape of Hadrian's Wall, look for bedrock, look for exposed rock. Yeah, it's very rare. The vast majority of stuff that you can see are smoothed, rounded hills. So which brings us on quite nicely to what those smooth, rounded hills might be made of. Okay. And these are glacial deposits. And to simplify what can be a complicated set of names, we can think of them as three types of deposit. Now, basically, they're just very wide, flat plains of boulder clay. Think of the all of the landscape between Newcastle and the coast, up to Morpeth and around there. It's just a huge expanse of boulder clay, very flat, very featureless, not much to see here. There's hardly any of that in the central sector of the north of Hadrian's Wall. There's lots of it to the east, and there's loads of it over at Carlisle. The other type of feature we can get are streamlined ridges and lumps and bumps, which are known by the phrase drumlin. Got some pictures. And finally, we get irregular lumps of stuff. Just, you don't know what it is. It's just loads of lumps, but it forms a rather sort of characteristic set of bumps and lumps, and just looks irregular. And it's clearly not bedrock, but you've got no idea what it actually means. How are we doing for time? We've got another 5 minutes and then we'll have some questions. Yeah. Okay, 3 pictures of glacial deposits, right? This is what the front of a glacier looks like. This is Geological in Iceland. And when you get to the front of a glacier, like this one, we can actually see some blue ice in here, some clean ice underneath. But by various processes, the material either melts on the surface or it's brought up by these little fractures from the base to the surface, and it forms this huge mess. Okay, very chaotic. And in front of the ice, you get lumps and bumps like this of just chaotic material. We get a floodplain in front of the ice, which is known as a sander plain or sander plain. And it just sort of gets washed around and broken up. Very chaotic ice fronts. This is another Eyjafjallajökull. Do you know the volcano that erupted a few years ago in Iceland, the big one? Well, this is just on the flanks of that, and it's where another glacier comes out to the off this volcano, and these are glacial lumps of volcano which have been reworked and rounded, some of them. That boulder, that the car's a little bit further away, it's a little bit unfair, but no, that boulder is big. It's the size of a double-decker bus, and rather unstably sitting on the top of a hill there. So glaciers can create boulder clay from anything from the tiniest materials right up to the biggest. And it tends to be very, again, it's rather chaotic and mixed up sort of material. Life becomes a bit more interesting for us when we think about drumlins. All of this chaotic material, either coming out the front of the glacier or from underneath the glacier, has the potential to be overridden at a later date by the ice as it keeps on moving and it expands and it contracts and things like that. And as ice overrides deposits which are already there, it has a tendency to shape them into streamlined features. Okay, and these run from in what's known as a continuum, from the tiniest thing, you know, a couple of millimeters across, perhaps a centimeter across, up to 100 kilometers. It'll just grow. These things can grow as big as they want to be. It all depends on the conditions under the ice. I think that picture on the top left is somewhere in Lancashire or somewhere like that. It's just a drumlin field. I've been mapping the drumlins in the Tyne Valley this summer, and I've got to over 3,000, and I'm probably about 2/3 of the way there. So there's a lot of these things around for us to find. So we might need to go and find some drumlins in the Tyne Valley. Okay, and this is just to remind us, I cannot emphasize too often that you get chaotic material. So it's not probably worth trying to work out exactly what the ice has produced. It's just to try and work out, is this streamlined or is this chaotic, sort of lots of lumps and bumps, or is it a flat till plane? Those are the 3 things you need to work out. Okay, after that you're flying. Last thing we can do a little bit about what's going on with water. Okay, so water is everywhere under the ice. The ice that we have in Hadrian's Wall was melting. It was melting all the time. Even when it was expanding, there's loads and loads of water around. Water at the surface, water in the middle of the ice, and water at the base of the ice. Like in this here, there's a little gap underneath the ice here. In this spot, there's a little cavity, and there's water dripping down and flowing through materials. So our landscape is also highly driven by water. And this is yet another glacier in Iceland, but this one's got quite a nice tunnel in the middle of the ice, and water's pouring out of that tunnel as it reaches the edge of the ice. You can see how black the ice is as well here. It's so filthy and dirty at its margin. And we've got a little pile of material here, and this was all quicksand in here. And yeah, the front of glaciers is not a place to walk around without a lot of care. So this water all comes out the front, and it can form lakes. So we often get lakes forming in the front of glaciers. So we see loads of lakes around Hadrian's Wall as well. Okay, so everywhere we look, there are lakes. There are remnant lakes, there are lakes which still exist now, and they're just a tiny fraction of the number that used to exist. Okay, and hopefully in the second part of this, after we've had a break, I'll show you lots of pretty pictures to prove all of this stuff. But I want to finish before we break with a fault-guided meltwater channel. Everybody rants on about this tree, right? And goes on and on and on about how famous this tree is, and it was the fact it was in a film and all the rest of it. And I just look at that and think, yep, meltwater channel, brilliant, classic meltwater channel, lovely meltwater channel. We left it with a picture of Sycamore Gap, and we can see there a hollow in the landscape. And when you're walking around on the wall, it's always worthwhile just asking yourself, when you see a feature of the landscape, how did it get there? What is it? I know geologists often concentrate on rocks and what the rocks are made out of, and as much as anything, I look at landscapes, and I look at how the landscape formed and ask myself, what does this bump or lump actually mean? These images are just grabbed from the internet. You know, Google search on the wall and Sycamore Gap, and you'll see dozens and dozens, if not hundreds, of pictures like this. And they're really good for doing geology, you know, especially in lockdown. If you can't get up there, just go and have a look at some pictures on the internet. So this is the gap that we were talking about. And when you look at it from the side, looking westwards, it seems to be a bit more elongated. It's not actually just a single thing. The walls obviously circled around in order to accommodate this gap. We've got some scree and things here which has fallen down, and in front of the wall itself there's a little scree slope in here. There's also a flat area there and a flat area there, and we start to see, when you look at it, there's quite a lot of features. Sycamore Gap isn't Sycamore Gap, it's Sycamore Gaps plural. It's part of a number of features which are all in exactly that bit of the wall. It just so happens there's a tree there, but if we go along, we've got a well, I guess, is that a mine castle or a fortlet? I don't know how you guys would know better than I do.
Mile Castle 37, I think.
Mile Castle 37.
Yeah, 37.
So we're now, that's interesting, we've got two gaps here. Okay, let's zoom back out a little bit more and see what else we've got. So again, we go back to Google Earth, and now we can see that actual fact, this whole features a little bit more interesting than we first thought. There's Sycamore Gap, there's another gap, there's another gap, there's another thing comes down just over here, possibly another one. We've got this area around here, which we now know these are lakes, yeah, and the lakes have then subsequently been infilled by peat. there is a lake there, and then there's another feature going over. So again, ask the simple questions. Can we see any bedrock? Well, actual fact, this area looks quite rough going across. There are some exposures of rock, in particular in the gaps where the erosion is. This feature coming down here, can't see any rock at all. Can't see any rock there. There's another lake. So what we seem to have is an alternation of lake, ridge, ridge, lake, etc. going on. And if we were to move across this landscape in this direction, you know, towards north-south, we would go over a whole series of ridges and hollows. And as you go around in Northumberland, if you travel north to south, you go ridge, lump, ridge, hollow, ridge, hollow. The roads go up and down, bouncing away. If you go from east to west, you don't do that. You go along one of the ridges. The roads are built along the ridges, the footpaths along the ridges. The travel in the past was always on the ridges because nobody in their right mind walks across a peat bog. So the Romans had this to bear in mind as well. The Staingate, for a large part, follows along the tops of ridges as well. So we can put this is 2 seconds in PowerPoint. It wasn't really any sort of great technical achievement, this, but just by starting to put a little bit of annotation on there. We've got a peat bog, which is probably a lake. We've got some channels coming through, slightly more complicated than I described. And we've got this feature comes all the way around this meltwater channel here, much more significant in size than the ones we can see over near Sycamore Gap. And we've got a lock there and an old lock there. There's quite a lot going on in this landscape. And it's often subtle until you get your eye in. But then once you start to see these channels and these drumlins and things like that, we suddenly start to see, actual fact, they're everywhere. So we'll go back to that original picture I started off the presentation with. And we've got a glacial meltwater channel coming through here. Rather so, it's not a huge thing. It's not majorly dramatic. In fact, you'd probably ignore it and miss it. You probably looked at it 100 times and just thought of it as a little depression with a bit of peaty bogginess in. But in reality, that's actually quite a major meltwater channel for the ice. So I look at it and I see that's a meltwater channel. And down in the bottom here, it's all boggy and flat, and there's all sorts of rough areas. But it is also, from a defensive point of view, if we look down here, it's been very difficult for people to get across the wall where there's a nice big cliff, but where there's a depression here, this would make it a much nicer and easier spot to get through the wall. And so we've got a fort very close by as well. I mean, it's all speculation. I'm not an archaeologist, but it's all good fun, isn't it? Okay, so moving on from that, I want to talk a little bit more now about maps and about how we might use software to explore these features. So what we have here is a map which is created in a bit of software called GIS software, and basically it's looking at what's called LiDAR data, which is height information. And this data is there's 1 pixel every meter across the landscape on a grid. And you can put it into some software and play around with it. Again, the software I've used to create this is free. The data is now freely available. Everything you're going to see is you could do yourself at home with a bit of concentration and hard work. So what we've got here is the wall. There's our little U-bends here in Sycamore Gap we've been talking about. And we can see when we look at this data, we can see that the landscape is made out of lots and lots of ridges, and there's some flat areas, like there's a flat area and there's a flat area. And some of the ridges are very sharp and well defined and other ones aren't. So I just want to talk you through the process I use to analyze the landscape, and that will just be perhaps an example of how this works. So there's our original LiDAR data, and often that can tell you a lot. I'm just going to zoom in this little bit in the middle here a little bit. So we're just going to zoom in, and now what I've got here is there's no information apart from the contours and open freely accessible free data from the Ordnance Survey. So and the pink there is just marking the boundary of the wall, and I think that's come from English heritage. And so again, we can that just sort of locates us. We've got Craglock there, and we can start to see that there's some valleys coming down off the wall. There's a meltwater channel here, and we've got some crags and whatever. So that's sort of useful. We can also overlay information on the bedrock. So this is the published maps from the British Geological Survey, which shows us the bedrock. So we can see these orange layers here. These are sandstones. It's a bit difficult to see, but there is a slightly darker blue in places. Very difficult to see, but that's limestone. And we can also see the pink, which is the whinstone. And we can see that in actual fact, the ridges are coincident with sandstone and sometimes with limestone just here, and obviously the big ridge itself. So it's another layer of information you can look at in this area. Now, we can get a little bit more sophisticated, and we can ask the software to tell us places where there are hollows. Okay, so this is picking out areas which are either flat or valleys. Yeah, so we're looking for valleys and we're looking for flat areas. So when we do that, we start to see stream networks coming up, and we can see that they all join up. So we follow this stream back up. One bit of it goes up to that meltwater channel there. Another bit comes across to this lake area, which then joins up with these meltwater channels here. This one goes round the corner, comes over there and goes up to this area. So again, it's just something you can do. None of this is my interpretation. This is just the software telling us where hollows are. Another way we can use exactly the same technique, but reverse it. We can ask the software to tell us where the ridges are. So the next slide here, same thing. We can, now we're just picking out where the ridges are. Okay, now the ridges, I said before, are often coincident with harder rock, sandstone and limestone and the windsill. What we're really looking for are places where they're not, where there are drumlins, yeah, where in actual fact the bedrock has gone in one direction and the ice has gone in a different direction. Okay, so that's just another image. So you can see we've got 5, 6 different images. We can overlay them on top of each other and play around and do all sorts of weird things. And as you look at each individual one, you see different aspects of the landscape. This is the one that usually gets people to go a little bit haywire. This is a every 1 meter contour is a different color. So as you go up a meter, you change color. Now, the reason I like this so much is that it shows a lot of these features, which are perhaps 2 or 3 meters high, 5 meters high, really jump out at you. Actually, I'm just going to show you. That's a drumlin in there. Yeah, that's a drumlin in there, that area. There's lots of smoothed features running across. So there are ridges where, like in this area, where we can see actual bedrock. We can see areas which are flat quite easily, like this area, and we can see areas where there's smooth lines running across. Yeah. Draw all of that together, and what I create are things like this. Now, up till now, everything previously was the raw data, right? No interpretation. That was just the way nature is. This is my interpretation of the data to try and identify features. The orange features, sorry there isn't a legend, the orange features are just moraines. They're just piles of gunk. Some of them are slightly elongated, but they're not necessarily very strongly streamlined. The brown are full-on classic drumlins. Yeah, they are elongated features that go along the ice. Sometimes they ignore the shape of the bedrock. In this area, they follow very closely to the shape of the harder rocks underneath. And then we get areas which are pink over there, which are just generally, there's so much gunk there, it's just a whole zone of stuff. Okay, so that's it. Then I'm just going to zoom out a little bit. So we start to see that as we zoom out, you can do this for the whole of the Tyne Valley. Hexham's off to the right, Hayden Bridge is down here, Holt Whistle's over there, and the wall comes through the middle here. The green features are drumlins which originate from ice which has come down the North Tyne Valley, and the brown ones are features which have actually come from the west. And the ice, you can see, sort of comes across and it sort of goes down into new buff areas, all sorts of complexity. Right, how are we doing for time? Still got 5 minutes? Yeah, show you one more thing if I can. Right, okay, so this picture that we've got here, I'm now going to overlay a model of the ice. So that's the same thing as we saw previously, but there's another layer on top, which is a model of the ice which I've created. You can model the ice in various different ways, but this is the one I've sort of come down to. And basically what I've got is a number of slides which basically show how the ice retreated. The ice was coming from the west and was basically flowing towards the east. It was basically flowing along various trajectories, and there's a margin here which is coming along the edge. We've got slightly higher ground here. This is the Tyne Valley, and I'm just going to basically quickly work through. It retreats a bit. This is Newbrough down here, and there's a little tongue of ice comes down over the side. Lots of lakes around the top forming. The lakes are relatively temporary features. They're formed by the ice but disappear once the ice goes. We retreat again, and we retreat again, and now we're into the position where the central sector of the wall has got this features moving around it in here, and we can come back and you see how it actually retreats. Now what's causing these patterns to emerge is literally the shape of the ice as it meets the topography of the landscape, as we sort of work our way backwards. And so this is Sycamore Gap here now emerging. We've got a tongue of the ice mass to the north of the wall. We've got a rather larger area which is to the south in the Tyne Valley. And then we get to a point where somewhere like this, and we're getting water coming off the side in these lakes, and the lakes overflow down. And the general trend of the water flow is from northwest to southeast, coming down towards the valley. And it either gets into a catchment which goes to Newbrough, or it gets into a catchment which ends up coming down towards Barton Mill. And then we zoom there. Okay. So let me. Okay, so I think what I'll do at that point is point you at there. Okay, so let's come back to our original slide. We've got drumlins and elongated features across this entire landscape. We've got meltwater channels which are just overflowing as water's flowing, trying to get away from the ice as it withdraws. Sorry, I was looking for something and I'd lost it, but I've just found it again. Okay, so here's a couple of images of a three-dimensional model, which was of exactly the same thing we've just been looking at. So we've got Sycamore Gap is just there. We've got a lake to the north of it, a lake to the south of it. We've got various bits flowing backwards and forwards. I can, oops, I'll just go to the next one. This is a view from the south of the same sort of situation. And we've got another view here, which is looking from the east. And this is a three-dimensional model which I can rotate around and play with. And you can do this with all GIS software if you've got the right set of information to play around with and the right colors and things. So, okay, so it's a complicated story. And if you look at any one particular bit of the wall, there's an interesting tale to be told. I'm just going to try and turn that off. How do I turn that off? And the way I do that is by doing that, and I go back to that, and then we go back to that. So what we have is our ice, which is either going backwards and forwards. We can fill the landscape or drop it out, and we just basically try and find at any one particular moment, where's the ice coming from, where's the ice going to, and what's actually happening at that point. And we can work out where the drumlins are and so on. So next time you go out on the wall and you are sitting there thinking to yourself, this is a rather beautiful, interesting landscape, and you look across, try and imagine that there's an ice sheet there. Try and imagine what the ice is doing. It's coming from the west to the east. If it's not bare rock, then it's a drumlin. If it looks like peat, then it's a lake. If there's a cut through one of these ridges, it's a meltwater channel. Okay, and there you are. If you do that, you'll understand the glaciation of of Hadrian's Wall. Okay. Right, I'll